Could you sit down in the aisles, please? Troublemakers again. Good evening, everybody. I'd just like to welcome everyone to the Architectural Association, those of you who are guests, those of you who are residents. It's quite nice to see so many of you. And I'm going to say very little other than absolutely delighted to have Dante and Nic Bini here today, and also their publisher, Will McLean, because this is on the occasion of the publication of a new translation of a book called Building with Air, written by Dante and about his work. And so afterwards there is a book launch, and you will see the books on the way out. So I'm just drawing your attention to that. But I'm now going to pass everything over to Will and Dante and Nic this evening.
Good evening. Welcome. It's my great pleasure to introduce the architect, engineer, inventor, Dante Bini, and his son Nic, who's also an architect and is continuing to develop the Bini family inventions, I suppose. Dante and Nic have also been accompanied by their family, and I'd like to thank Adria, Anna and Kimberly for joining us here. It's very nice of you to all come, so thank you. It's great to have you here. Also, quite a few of my family too. I just have a few thank yous as my role as publisher that I'd like to make. Firstly, Dante, for allowing me to make an English edition of his book. I'd like to thank my family, Samantha, Bert and Frida, for their support and patience. That was my wife, actually. She didn't mention that she's married to me, but anyway, whatever. And so I thought of it. And also my colleague, Pete Silver. The wonderful design of the book is by Mark Boyce, who's on his way, but who's my brother-in-law, or soon-to-be brother-in-law officially, but occasionally I do invite other people who are not related to do things. And the design of the book really captures the spirit of Dante's unique body of work and his ideas of construction automation using the power, the inexpensive power, of air. Last year I spent a couple of days in Italy with Bini, with Dante, discussing the contents of the book. Whilst he drove us at high speed, adjusting his scarf like this, just at high speed, showing me some of his early domes, which included swimming pools, sports halls, and eventually a nightclub designed in 1968. Good date. We met the owners of the nightclub, and we then sort of spent the afternoon with Dante advising their son, who was about to study architecture, and that is Dante Bini. He is not interested, I think, I may be wrong, but he's not interested in his buildings as precious structures, but asks how we as designers can think differently about our role in society in servicing the needs of humankind, and in that respect we must see his work in the context of other great humanist designers, structural artists such as Fry Otto and Buckminster Fuller. So this is turning into a bit of a rant, isn't it? So I'm sorry about that. It's nearly finished. So now Nic is going to introduce his father and give a kind of context to the aims of the work and a bit of the history of Dante's work. And then the maestro himself will give a short talk and answer questions. Then we can have a glass of wine and you can all buy books. So I'd like to thank you. It is obligatory, the last bit. And I'd like to thank Belinda at the AA for organising this event. And I'd also like to thank Charlotte and the bookshop for hosting that bit. So thank you very much. And Nic, thank you.
The old guy start first. Well, ladies and gentlemen, good evening. First of all, I wish to thank very much our hosts at the American Association of Architects, which I believe that the oldest one in UK. And I'm very honored to be here, knowing that this is one of the oldest in the world. But I like to introduce also, I like to thank very much the person who made all of this possible, Mr. Will McLean, who has published also my book through the Bibliothèque McLean, and which is produced in a very pleasant format. And thank you very much for selecting the designer of this, Mark. He's a good guy. I think he has done something very important. But the aim of this book is to encourage students of engineering and architecture to be the protagonists, the conscientious protagonists of our challenging times and be able to interpret our times. This is the main reason because I wrote this book. Your presence here is very important to me and to my son Nick, because we believe very much in what we are trying to transmit to the architecture field. In particular, Nick is going to present what we have done in the past and what he's doing at the present. And he made a big contribution in my book, and I don't want to be too long, and I like Nick to come here to complete this conversation. Thank you.
Will, thank you very much. It's an honor to be here. Can't believe it. Will, thank you so much. And since you kicked us off on this, and we're Italian, thank you to my family, thank you to my wife, thank you to my mamma, without which none of this would have been possible, and of course my aunt, my cousin. But the book is awesome, and it could have been called, The Exciting Life I Led, and Professional and Personal Life I Led when I started thinking differently about architecture. But somehow, Will, you didn't think that was quite as catchy as Building with Air. I have to agree. But it is true that when Dad started thinking differently about architecture, all this incredible stuff happened. So before looking at what my father did, let's take your Oxford Dictionary as a good means of beginning to look at what architecture is. So the Oxford Dictionary says that architecture is defined as the art or practice of designing and constructing buildings. And truth be told, on the design part of things, in the last 150 years, I'd say we've done pretty damn well as architects. We've had movements, we've had counter-movements, we've led the charge in the creative fields a lot of times. There's a lot been going on, a lot of it has been coming out of this country, and it's exciting to see what has happened in the last 150 years from a design standpoint in architecture. But again, looking back at the definition, that's only half the equation, okay? So now let's look at the other half. What have we done as architects in developing new and interesting and conscientious ways of constructing, right? Well, 150 years ago, little more, here they built the Crystal Palace. 90,000 square meters, 5 stories tall, glass facade, curtain wall, totally modular steel frame. We haven't really come far. I would say that we haven't really come anywhere in terms of construction in the last 150 years. We build different shapes, but we build them in the same way, okay? So, you know, getting back to this definition of architect, we've only been doing half the job. Now, where is this, what is construction? How important is it? Why should we look at it? Well, by definition, or statistically, I should say, it represents 10% of the world's GDP, so it's a huge industry. 1 out of every 7 jobs, it provides 1 out of every 7 jobs in the world, and it represents 1 out of 3 basic human needs. You know, we spend most of our time in buildings, we keep all our possessions in building, we house our families in buildings, okay? So this construction thing is kind of a big deal. Now, to put it in context, let's compare construction and the evolution of construction over the last 150 years to 2 other big industries. Now, these aren't industries as big as construction or as impactful, but still, they're pretty big, communication and transportation. 150 years ago, more or less, they developed the first telegraph. Now, we've got little supercomputers in our pocket. We can research practically all of the world's knowledge at our fingertips on our computers, and we can reach out to anybody that we'd ever like to know. So, you know, it's pretty easy to make the argument that we've come a long way in 150 years in communication. Similarly, 150 years ago, they invented the steam engine, or also they just patented the bicycle. Today, we've got supersonic jets that are incredibly high performance. We've got, you know, high performance electric cars. We've got a Martian rover. So clearly, we've come a long way when it comes to transportation. So what's been going on in construction? The donut, that's an American thing. But, you know, my argument is very, very little, relatively nothing when you compare it to these other industries. I mean, honestly, we build, if you, the Crystal Palace, 90,000 square meters of it, was conceived and completed in 6 months. Can anyone think of a building even half the size that was executed from concept to cutting of ribbon in even double that time? Right? It's kind of wild. That Joseph Paxton was so far ahead of his time, and that we've really dropped the ball since then. Now, the interesting thing about this is that construction, like I was saying previously, is kind of a big deal, and we need it more and more, and we need it to perform better and better. The number and strength of natural disasters doubles roughly every 10 years, and that's not to speak about the strength of them. We all know this, it's tragic, it happens all around the world, whether it's a fire, an earthquake, high winds, tornadoes. We're not treating nature well, it's not treating us well in return. So buildings have to get stronger. Our lives depend on it, so do our children, so does everything we own. Now, in terms of affordability, construction also, you know, is questionable, at least, because 1 out of 4 people today is either homeless or living in substandard housing. So we have to come up from a humanistic standpoint with a better way of building. We have to. 1 out of 4 people in this room statistically should not have a house to go home to. And building is by far the worst polluter, accounting for 50% of our natural resources annually. It uses 40% of our energy. 40% of our carbon emissions are produced by construction, and 35% of our solid waste stream. This is a very, very large, wasteful industry, and nobody's talking about it or doing anything about it. So looking at this, remembering how well we've done in design, you know, the question is, how do we as individuals rate construction? How's it going? How much have we done in the last 150 years? Do we need to think about it? My opinion is that construction is not safe enough, not green enough, too costly, excuse me, and technologically antiquated. And I think the facts bear that out pretty solidly. So what's interesting is that, I was part of I still am part of the problem rather than part of the solution. But what this book is trying to teach us, and you can just see how thick my head is, because I only caught up to this about 5 years ago when I had children of my own. What my father is telling us is, you know what? Let's look at different ways of construction, because it's cool. There's a lot of opportunity. It's a big industry. There's a tremendous need. If you care about people, think about construction. If you want to make a lot of money, think about construction. Even if you want to differentiate yourself from the masses of talent that are all looking at design. I mean, I have a blog, and I've been posting great architectural firms for every day for the last 5 years. There's so much talent all around the world looking at design. If we could take a small percentage of that talent and dedicate it to construction, which is by definition half of the equation, without forgetting about design, why? It informs design. And that's what this book is about. Now, the cool thing about that is all the things I've mentioned. But let's look specifically at how my father did this, executed on this idea of building with air. As you can see, and as is described in greater detail in the book, my father invented this way of using low air pressure, which is less than 1 psi, exactly more like 0.4 psi, which is approximately the amount of pressure that you use when you smoke a cigarette, i.e. practically nothing, to lift and shape reinforced thin shell concrete domes, okay? Now, these domes are poured at ground level. And I remember when I was at grad school, I showed our structural teacher, who was a great innovator at UC Berkeley, a movie of a 40-meter diameter dome going up in an hour. And it's actually this project, which you can see online on my father's site. Each of those domes came up in an hour, and he couldn't believe it. He said, this is impossible, and he actually turned the thing off and had a talk with me afterwards. I was like, dude, that's not like animation. I mean, it was like 85 or something. It happened. Don't tell me it's not impossible. We've traveled around the world because of this technology that my father invented. And but it's incredible. That really shows you like how far ahead of his time he was. Amongst his works, as is easy to sort of point out, is this fabulous dome that he built in Sardinia for Michelangelo Antonioni, who's the Italian director who did Blow Up, and at the time was married to Monica Vitti. And it's a super cool dome. Actually will be featured in the Biennale this year in Venice, which is awesome. But he didn't stop there. He invented several other systems, including this triangulated three-dimensional space frame, which is also inflated and entirely demountable. So let's say you need a field hospital, or in this case, a temporary structure. You inflate this thing, the components expand. If you think about like a umbrella, click into position, and then come down and rest upon themselves. It's obviously a triangulated structure, 3D space frame, so it's very strong. And then all you have to do is unclip all the frames, and the thing sort of folds into itself, and you pack it away and reuse it, 50, 100 times. He didn't stop there. He went on and, working with a Japanese firm, developed this concept for a mile-high city infrastructure. And those things that are in the pyramid are actually skyscrapers, like 50, story tall skyscrapers. And the nodes and triangular members are ways of getting people or other products throughout this sort of 3D city. So all sorts of interesting ideas, all explained in the book. And it's cool. And one of the things that's cool about thinking this way, and the opportunity we all have when we start thinking this way, is that we, have pretty good company of people who all thought differently and had fun and did good stuff. So that's the thing that my father's encouraging all of us to do. And so that this isn't totally abstract, I decided to illustrate an example of how I tried to, 5 years ago, start cluing in and take some of his thinking and evolve it in some way. So I had this sort of, technological know-how, all these various construction systems invented by my father. Now, a lot of these systems were no longer code compliant, but so I had to look into codes and evaluate international codes, make sure that whatever I came up with conformed to those codes, because you have to be practical. And then I also looked at, with my team, material improvements, of which there have been many, and compared different materials, availabilities, etc. And then tried to also look at this from a market standpoint, understanding the market, speaking to people that know a lot about a lot of things that I have no idea about, and learning from them. And developed a series of systems, again, based on this concept of using air pressure to lift and shape reinforced thin shell structures. Binishell System 4 is a 900 square foot square-based dome where the openings result automatically from the construction process. It's a very, very green system because it's got a, like all thin shell structures, a thermal bridge-free building envelope, which is massive. That alone accounts for reducing carbon emissions and energy use by approximately 79%, according to the International Energy Agency, and that's where it begins. So it's a very green system and usable for things such as housing, education, and more. Binishell System 5 is a low-cost housing system, a 350 square foot, about 35 square meter rectangular vault, extremely affordable, and also very green. But as President Clinton's group said, one of the things that they really liked, aside from the speed of construction, the strength, and the fact that these cost a lot less than anything else on the market, it's all built, it's all very simple, so it can be built with local labor, local materials. And that enables you to build up the infrastructure as well as the local economy, let's say, after a disaster. Then, in a more expressive, sort of architecturally based solution, we developed Binishell System 6, which is practically any size, any shape, very flexible, still very green, and highly affordable in comparison to traditional structures, and it can be applicable for homes, resorts, and other infrastructure projects. The net result is that the costs are reduced. Now, by this I mean environmental costs, because we use less materials, less than half the materials, and also bottom line costs. Well, excuse me. Costs in building, of course, the two biggest line items are materials and labor, so we use less of both. And then, because of that, it costs less, but at the same time, it's far more green, which is increasingly important. Why? Primarily because of the efficiency of the building envelope. It's a thermal bridge-free envelope, and as I said before, that really impacts in a very positive way the energy use of the structure, decreasing it by around 75 to 80%. And then there's minimal waste. There's no cut material on site. It's all poured. You just pour what you need. So you get at most a wheelbarrow of waste per building. And that's an advantage for cost and from an environmental standpoint. And it's far faster, which is cool because, you know, if you've had a disaster in your country and you need to house people because they're getting diseases, it's important to do this, impact this quickly, but also because if you're a construction company and you're looking at your bottom line, if you can build things 3 times faster, that means that you can do 3 times as many projects in a given year, which is really all they think about. So you feed into that, but you're feeding into that with a better product. So in the end, everybody wins. And it's far safer. We all know that traditional construction has right angles, beams meet columns. That is actually the least structurally efficient way of building. Interestingly, that's how we build and house our children and all our precious things. A dome, on the other hand, instead of concentrating energies and in very inefficient ways, a dome distributes energy in the most efficient way possible and therefore is far more materially efficient, which is why we use less materials and impact the environment less. So what have we done with these things? A couple of examples. We've got an exciting project in Malibu for one of the famous actors out there, one of the most famous actors out there. And this is going to be his family's home. And we're looking at interesting ways of developing the interior as well as the exterior, which is quite exciting, and both innovative from a design and sort of environmental impact standpoint. The net result of this building will be that at minimum we'll reduce energy usage by around 85%. Harvard's going to be doing a study verifying all these numbers, but this is what we're coming up with so far. At minimum life cycle reduction of 75%, overall construction budget reduced by about 35%, and at least a 65% reduction in the overall construction schedule. We also are looking at low-cost disaster relief housing in the Philippines, using System 5, and there will be reducing energy use by around 70%, life cycle impact by about 55%, costs by about 45%, which is exciting, and then schedule reduced by about 75%. So again, it's exciting and important to, I think, absorb the lessons of my father through this book about thinking differently about architecture, and to use local slang, think out of the box and carry on. Thank you.
Before we have a drink, would anyone like to ask questions to Dante or Nick?
Or both.
Yeah, come on, you've got to come on. Are there any questions?
Okay, yes?
Hello, how many of your Binishells are there in this country?
In this country, there are only few of them, but one remains, and is in Marvin College.
I know that one. That's why I was wondering if there were any more.
Yes, this is.
And there was one in Cambridgeshire, Milton Hall.
This is at the College of Girl College
Yes.
of Marvin. Sorry? I'm sorry. Okay. Yes, this is it. I mean,
And
this
you,
is.
you did one in Milton Hall, I think, as a sports building.
They actually, we have licensed a company here in UK many years ago, and the company names was Parashell. And they have built, I think, 4 or 5 of these structures. But the more important one is in Marvin. And it is a beautiful building designed by a local architect. Godwin, I think is the
Yes,
name.
Michael Godwin.
Michael Godwin. Yes, it is listed in. I was very impressed about the fact that was listed
I
because,
wondered what you thought about the listing, because I'm from English Heritage, so I do know the building.
yes, and I think that another building of mine, I mean, Binishell's, will be listed in Italy. The house of Michelangelo Antonioni that you have seen before will be listed as, no, there is an organization in Italy called Sovrintendenza ai Monumenti, which try to preserve the structures that are more of some significance. Yes?
Hello. I wanted to know, sort of in the beginnings of the design, when you were in the process of this construction, how did you, it's more of a factual thing, how did you get the banks and developers to pay for it? Did you invest in it initially, or how did it gain traction?
Well, the history of the Binishell's process and all the process that started from the Binishell's are very clear in this, illustrated in the book. And it is a long story. It's about many. Yes. My son says, why you don't tell about the beginning of the story? The beginning of the story is the following. I was playing tennis underneath those inflatable balloons. It was in Bologna in the winter time, and it was a long fight with my friend Sassoli. And at the end of this hard tennis game, we were unable to exit the balloon, the inflated balloon. And we could not believe it. To spend the whole night there was not a very good proposition. So we pushing the second door, because as you know, there are two doors in those inflatable balloons. Pushing the second door, we were unable to open it. Finally, we found out that a meter of snow has fallen down during our game. And immediately I realized that I could not feel the extra pressure due to tons of snow on top of the dome. So since I was working on a thin shell structure in my thesis, I immediately realized that it was possible to lift the entire structure that I was designing using only a very limited air pressure. Indeed, when I was playing, I could not feel the additional pressure for this enormous amount of, because this was 2 tennis courts covered. So you can imagine 1 meter of snow all over. And this was the beginning of the light that came out from the bulb of my brain.
Thank you.
Can I follow up on that? I'm still unclear as to how it's made. So there's a plastic or a sheet or something that you pour the liquid onto, and then slowly, how is it actually, can you explain the process of it inflating?
Okay, the process is the following. You have a ring beam as a footing system. Then attached to this ring beam, you have an inflatable membrane, 1 millimeter thick, made by neoprene and nylon or PVC reinforced. And you imagine to have this balloon deflated on the ground. You fold it, you put some what we call fish scale to prevent the steel reinforcement to make too much friction with the membrane that will be lifting the entire thing. Then you pour concrete on the steel reinforcement, the amount of concrete that you need for the entire dome. So it is much bigger in the center and is reduced to the periphery. Then you just inflate and everything comes up in 60 minutes. The main problem that I I realized from the beginning how to control a wet concrete to be lifted by an inflatable balloon, because no, it was the first time it was going this way. So I was following the situation with trepidation. Then I discovered that if I was able to provide a force opposing the inflation process, I was able to control the inflation system. So I invented for the first time a spring, a sort of layout of springs, metal springs, in which I fed inside the steel reinforcement, which was hooked in one side and free in the other side. In each spring, considered to have, for example, two steel reinforced, two rods in each one spring. During the inflation process, the rods could not go out from the spring, so they would go up exactly in the position that we wanted to obtain. Indeed, I don't have the picture of the sequence of springs, but it's made in such a way that you have the absolute certainty that the spring steel reinforcement goes exactly. You see this in this picture, in the picture number 1, you see the pattern of steel springs, steels with steel reinforcement inside. So after you pour the concrete, and you cover, in this case, with a second membrane, which is used for vibrating the system. Okay, thank you. You see, you have 300 tons of wet concrete, 300 tons of wet concrete, 25 ready-mix concrete trucks, to give you an idea. The first time I did it, I could not believe that I was able to raise this with a blower of this size, so negligible pressure. So this is covered with a second membrane only because we want to vibrate. Because the problem is this: when you lift the reinforced concrete, the concrete disgregates a little bit. So you need to recompact the concrete to make the structure solid. So initially we smooth by hand, but when you have such big dimensions, you see those are people. This is 36-meter diameter dome. It's bigger than your St. Paul dome. And when you have this coming up in 60 minutes, in 60 minutes you have to finish the job. Because otherwise you produce a skating rink. So this is a limit. So using this concept to use the control of the uplifting and the cover for the to vibrate the concrete, you produce a real self-reinforcing process. But they can listen to me. Okay. Sorry, I'm sorry. There is a movie. Okay. There is a question. This lady wants to ask a question, I think.
Yeah, I had
Forgotten.
It's coming back. On more the development of this design idea, because I felt that you were bringing up the scale of the design, which made me feel a bit uncomfortable in the sense that you were reproducing the design in many places. And it actually lacked, I prefer to see the building, the design idea in one slot. But when you see all of them together, I kind of lose the idea of connecting the design to the architecture. I was wondering if there was some way you...
I think you should answer to this question because it's more architectural than technological.
So just so I understand better, you're saying you like domes better than other shapes?
No, I'm just saying because...
Sorry.
No, that the reproducibility of the same
Oh,
dome.
multiple times.
I'm just questioning if this is actually getting the design closer to the fight of making architecture, because I find it really interesting to challenge the fact that architects are not thinking in this design way,
Yep.
which can be really interesting. And so
the thing that, you know, interests me and what I did my thesis on when I was at grad school is this massive need internationally for low-cost housing. And so when I thought about, you know, with a friend of mine who's an engineer at the English firm Arup, we went to grad school together, and we sort of thought, what is the most efficient way of building? How can we think about a way of, you know, providing homes that, you know, fit a lot of bills and check a lot of boxes? And what we found, you know, is that this idea of building domes is extremely efficient. Why? Because domes are stronger, therefore you use less material. Concrete is extremely environmentally efficient, while at the same time being the product we make most of as a species.
They don't burn.
Si, si.
They're fireproof.
And then the resulting structure, like I said, is very strong in all sorts of different ways, like Dad's pointing out, fires, earthquakes, high winds. And so the next challenge is, how do you aggregate them? And I think that's what you're getting at. And I'm not suggesting that either of these two ways are, you know, award-winning solutions. But what we're trying to do is think about, when you do a lot of these things, what do they look like? And, you know, the argument can be made that the, you know, Hellenistic concept of a pitched roof and a square box under it is not necessarily objectively attractive, nor representative of home or any of the cultures that it ends up being implemented in, other than possibly Greece. So, you know, if you provide another solution that costs, you know, let's say half as much, but is greener and stronger, you're heading in the right direction. But one of the other things quickly that I also wanted to look at is the fact that domes are something that especially difficult to sort of marry with the concept of home. So what we've done is taken the circular plan and turned it into different and sometimes rectilinear shapes to facilitate, you know, ordinary lifestyles. And it's a step towards improving the environment, providing safer homes more affordably and efficiently. When we presented it to the UN or the Clinton Global Initiative or the World Bank or the Inter-American Bank or the Inter-Asian Bank, you know, it was thrilling to hear them use words such as, you know, the golden egg and all this kind of stuff, because it's really significantly cheaper, far stronger, and quicker. But then, as mentioned previously, it uses, so simple that it uses local materials and local labor. So I think there's something there. Is a potential for improvement? Absolutely.
Yes. 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 Go ahead.
Why don't you've
No.
got a microphone in your hand.
If we can stay on curves, maybe. What is your vision about construction? Should we go towards curvature or should we stick with lines?
Well, look, we should look at all sorts of different solutions. A lot of, you know, this system, or this family of systems, is criticized for being a low to mid-density solution and not a high-density solution. And that's fair enough. There have been 4-story Binishells built, but you can't build this as a 10, 15, 20-story structure. And so it's not the solution for everything. We're looking at different ways, and Dad's developed some systems for building high-rise buildings with air pressure and vacuums in concert. And so there's solutions, a number of solutions, especially if you can crawl inside his head. But it's exciting. And, you know, I like curvilinear. I think it's very sexy that this system is not designed by me, but is designed by nature, specifically Pascal's laws. And that, to me, makes it more objective than, again, the Hellenistic pitched roof solution. And, you know, you can say that it's a little bit more pan-cultural because it's not, you know, it's not biomorphic, it's biologic, you know, so it's quite interesting from that standpoint. And it turns out that, you know, a lot of other designers are looking at curvilinear too, but a lot of great designers are looking, and a lot of great design has been developed as rectilinear. I think there's room for both. But the main thing is, let's just think of the other side of the equation, because construction is a big deal.
Yes. No?
Oh, yes.
Yes,
I'd like
now.
to keep it on track, and thank you for your
Thank
very
you.
interesting presentation. Last year, in the month of July, I found out that IKEA had a similar idea than yours, and when you mentioned that you talked to the UN about it, I'm very interested in their opinion, because I actually know IKEA's costs for what they are trying to do in changing the tents that house political refugees and, you know, zones of conflict. So they're talking about designing a low-cost house that in prototype phase costs around 10,000 euros, and that would then, when they said that when they will begin mass production, it will cost around 1,000 euros per unit, which is, in my opinion, around 10 times more than you pay for a tent. So I would like to see what's your take on this?
So we don't know about the mass production element, but in working with a company out in the Philippines, our prototyping costs for each unit is somewhere around $2,000 for a finished structure. But the additional advantage versus prefabrication, which is, you know, as old as Stonehenge potentially, is that it's all built in place, and therefore, you know, the material is developed by a local cement company, which keeps the money locally, which reinforces this thing of building up the local infrastructure and the local economy. Plus, when you look at the environmental impact of prefabrication, you know, prefabrication begins in the Swedish plant or in a local plant that's built to build these things down the line. And the overall efficiency of a prefabricated structure is very comparable to a traditional structure versus a thermal bridge-free envelope provides additional advantages. So there's rooms for all sorts of different solutions, and it's wonderful that a forward-thinking company like IKEA is looking at low-cost housing. What's surprising to me is that, you know, more students, more architects aren't looking at the big picture of low-cost housing and looking at the opportunities to do well that it presents.
Yes? Microphone.
Hello?
Yes.
Well, it's obviously a very efficient and beautiful building and design system. I'm actually more interested to know about the interior, and I'm wondering, for example, about this. Is this a one-story construction? Are they all effectively bungalows? Or have you tried to divide it in different stories? And if you do, then how you do it? So you blow up the dome, and then if you have added other stories, sorry, I've missed the beginning of the lecture, so perhaps you've shown it before, and then how do you do it, and how does it work?
Very relevant question, and my father will answer. But yeah, you can build multi-story. The stories that are built on the interior are built traditionally, and then the shell is the thing that's different. So there's room for improvement there. And that's what my father worked on for a period of time.
So the interior structure that is built in a traditional way is freestanding on its own, is in a way structurally detached from the exterior shell, right?
That's one sort of simple solution, but there's more sophisticated ones.
I wish to remember a very interesting project that I was requested to design at the former Soviet Union. They wanted to build 14 million houses built in wood, not in concrete, and with the shape of a traditional house. So I said, have you been able to build a square base bubble soap or not? Then I stopped talking in this way because the $14 million was an important subject. And I designed a traditional house built by air pressure after all the components were on the ground. And I built in California, and I made a model. I brought this model in Moscow, in front of the mayor of Moscow at that time. I was able to show that in few seconds, I was able to lift and shape 16 pieces of prefabricated components of a square-based house, traditional made, and built only using air as energy. Then, unfortunately, fortunately for them, Gorbachev came to power and all my project was shelved. But the point is this: you can use the concept to use air pressure as energy for everything. Before I was making something like this, because in Japan I built a model of a multi-story building using compressed air to lift to the second floor, a floor, along pipes, along vertical supports. Then I was able to make vacuum between the first floor and the second floor, reaching the first floor and going up like this. We were able to build a multi-story building in a model. So it is possible. I mean, if we start thinking in a different way, this is what I was trying to say before. We have to use a different perspective, a different philosophy in construction. In my case, I was lucky to find out that the air pressure was an incredible power to use and very green for building. But you can use different technology. I don't know, but don't stop thinking that what we read in the book is the only Bible that you can follow. Use your imagination and proceed. If you see in my book, you'll see a number of building systems that I've been using, I have built in different parts of the world, not only dome. The dome was, the Binishell was the first one. But you will see a number of construction systems which were originated by the Binishell. But then they found different avenues. And this is the beauty. And I don't think that this is the only way. You know, when someone is trying to open the mind and think out of the box, you'll see something extremely interesting.
I think on that note, I think that's fantastic.
Thank you very much.